In this video, we're going to talk about curvilinear coordinate systems. They are just like the Cartesian in the sense that they are defined based on a frame, which gives you an origin and cardinal directions on which you can base the coordinate systems. But the rules that you're using to label the positions in space are different. So you're already familiar with the planar polar coordinates, cylindrical polar coordinates, spherical polar coordinates, I hope. If not, you should definitely review them. I will make a short review video later that deals with the cylindrical and spherical polar coordinates. We're going to talk about planar polar coordinates here. These are not in any way the only curvilinear coordinate systems you can imagine. Here are a few others, which you may or may not have seen, but that have their use in some specialized applications. These images of the coordinate systems that you see here have lines in them. These are known as coordinate lines, which I just briefly defined for you here. A coordinate line is a line that's obtained by varying one of the coordinates and keeping the others constant. And one thing that you can note here, in all these coordinate systems, although you can't see it for the cylindrical and spherical coordinates, is that the coordinate lines always intersect at right angles. So that's true for the polar coordinates. I've indicated a few here, but it's the same everywhere, and it's true here as well. When that is the case, when the coordinate lines intersect at right angles, we say that the coordinate system is orthogonal. And all the coordinate systems that we're working with here, and that we will be working with in this course, are orthogonal. If a coordinate system is not orthogonal, it's known as a skew coordinate system. They have their uses, for instance, in general relativity, but we won't encounter them, so I'm not going to discuss them any further. What I will do now, though, is look at the planar polar coordinate system in some greater detail. Like we discussed before, they have unit vectors, like that. And we can pick a particular position in space that we want to then find labels to. The labels are going to be, or the coordinates are going to be r and phi. And we can then indicate this position by a position vector. So now we have to specify the rules for obtaining r and phi. And those are pretty simple. R is the magnitude of the position vector. And phi is the counterclockwise angle from the positive x-axis, rather from the x-hat unit vector. So this is phi right there. Now, using the same frame, we can also define, of course, a Cartesian coordinate system that has the same origin as the polar coordinate system, and that means we can write down a transformation from Cartesian coordinates. And that's as follows. So r is the square root of x squared plus y squared. Phi is the arctangent of y over x. Although you might have to add a factor of, or you might have to add pi to this in order to be able to correctly label positions in the third and fourth quadrant. We can also go backwards and find an inverse transformation. Now, so far so good. The next step now is to figure out how to deal with vectors in a curvilinear coordinate system. And that's perhaps not completely obvious. In order to see how to do that, we have to think about what the motivation is behind using a curvilinear coordinate system in the first place. It is really to simplify calculations. And they're introduced because there is some symmetry or some specific geometry that we'd like to replicate in our calculations. So when we work with vectors, we want to also capture the same symmetry. In order to do that, we do as follows. At every point in space now, we will define a local frame where the unit vectors are aligned with the coordinate lines. So that's the first step. And then when you want to work with a vector, so let's say that we have a vector here. When we want to work with a vector, we need to decompose it then into its local coordinates onto the unit vectors of this local frame. Okay, so for the specific case now of the planar polar coordinate system, we will have a unit vector that's aligned with the r hat direction, with the r directions, that's r hat, and we will have one which is aligned with the phi direction. So that is phi hat right there. And then Q here now, if you want to find its components, what we'll have to do is decompose it into the theta direction and into the r hat direction, like that. Right. So in this case, we'll get that Q equals sum QR times r hat plus q phi times phi hat. Now, I said earlier that the vector as a vector doesn't depend on position, and that remains true. If I take this q vector and move it over somewhere here, it is still the same vector q. However, the local frame that consists of r hat and phi hat does change. So even though the vector doesn't change with position, actually its components do. So that's something that happens in a curvilinear coordinate system that you also have to keep track of as you work with it. And in order to do that, we have to come up with expressions for r hat and phi hat. The easiest way to do that is to find expressions for them in terms of x hat and y hat, the coordinate systems of the global frame. So just to be clear here, we have this is our global frame. Over here we have the local frame. In physics, when we talk about the frame, by the way, we will almost always mean the global frame. That's the one that says the origin of a coordinate system, and that's the one we're talking about. This frame here that moves along with the object, sometimes known as the moving frame, is usually not talked about as a frame, but mathematically it definitely is a frame. So I'm going to now decompose r hat and phi hat onto x and y. So we know that r hat is going to consist of some x component in the x direction, r hat x, plus r hat y in the y component, and in the y hat direction. That just comes down to taking the projection of r hat onto x hat with the scalar product, and the same thing in the y direction. You can write that just as an ordered pair. R scalar x hat, comma r hat scalar y hat. And if you just take that scalar product, it's easy to see that that becomes equal to cosine phi comma sine phi. Okay, and we can do the same thing for phi hat, and then we'll get that that is minus sine phi cosine phi. So this is the price you pay for working in a curvilinear coordinate system with vectors, and that is that the unit vectors, the local unit vectors onto which you want to decompose your vectors, actually depend on position. This can lead to some subtle issues that I will show you in a minute. First, though, I'm just going to ask you a question. This is something that we'll do with some regularity in these videos, and then we'll discuss it later in class. Let me just rewrite these expressions for r hat and phi hat, and then I'll ask you the specific question. So we have, like I said, that r hat is cosine phi sine phi in the x hat y hat frame, and phi hat equals minus sine phi comma cosine phi in the x hat y hat frame. Okay, so I found this argument just by doing this projection. You can also find these expressions from these transformations. You can start from the Cartesian, the transformations from Cartesian coordinates to polar coordinates, or the inverse transformation, and you can find these. You can find an expression for these unit vectors mathematically. The question is how. So that's a question that I'm asking you. How can you find the expressions for r hat and phi hat starting from these transformations? That is, from r as a function of x and y, and phi as a function of x and y, or from x as a function of r and phi, and y as a function of r and phi. This is not an entirely trivial question. So if you manage to solve this, you'll get an extra gold star. As a hint, I can let you know that there are actually two different ways that you can do it, at least two different ways that I know of. You can either follow the coordinate lines, so you can do exactly follow the expression, the prescription for how a coordinate line is constructed. Vary one coordinate, keep the others constant. Or you can look at the directions that are perpendicular to the coordinate lines. And they should give you the same result in this case. Okay, so that's the question for you. Now let's move on to some of the difficulties you might run into when you work with vectors in curvilinear coordinate systems. So here is a general coordinate system, and I'm going to have two different vectors in here. So here are two different vectors. Let's call them R1 and R2. They have different angles to the x-axis, phi 2 and phi 1. But we'll say that they both have the same length, r. Okay. Now, in order to decompose them, the natural thing to do is to decompose them onto the unit vectors that are associated with the positions at their tips. Right. So we'll have an r hat here, a phi hat there, as well as an r hat and a phi hat there. Now, since both vectors have the same length, their expressions in terms of r hat and phi hat are actually the same. We get that r1 is r hat, and we get that r2 is r hat. But at the same time, we can see very clearly that r1 is not the same thing as r2. So how does that work out? How is that possible? We have the same expression for both of them, yet the two vectors are different. What we haven't taken into account is the fact that r hat depends on phi. So really, if we want to write out the full expression for this, we know that r hat is actually r times r hat, which depends on phi 1, and r2 is r times r hat, which depends on phi 2. But oftentimes you don't write that out. But when you're working with curvilinear coordinate systems, you have to keep in mind that the unit vectors do depend on position. And that has effects here, clearly. So to be a little more general about it, in general, we can take a vector A and we'll decompose it onto different unit vectors. Like so. But we need to keep in mind that A1, E1 hat depends on a number of different things. So depending on what we are looking at here, A1 could depend on the position R, which can depend on time. But it is also true for E1 hat. It depends on position, which can depend on time. It's also possible for E1 hat to depend on time itself. This is a local frame. E1 hat, which could be R hat, for instance, will depend on the local position. But nothing says that the global frame, the frame that you're physically working with, has to be constant in time. We've seen before that that can move with a constant velocity. It can accelerate. So if actually the global frame changes direction, then E1 hat can also depend on position. Okay, so let's just write this out explicitly here. So the position dependent of A1 can depend on the position of the object we're working with, or it can depend on the origin of the global frame. The unit vector can depend on position if the coordinate system is curvilinear. And it can depend on time if the global frame changes orientation over time. And if something changes orientation over time, that really is the same as saying that it rotates. So specifically, this means that if we're working in a Cartesian coordinate system that doesn't rotate in time, and if we take the vector A and we take its time derivative, that amounts to taking the time derivative of all the components. Like that, for instance, since x hat, y hat, and z hat are fixed. But in general, we have that the time derivative of the vector A is A1 dot E1 hat, etc., plus A1 E1 hat dot plus A2 E2 hat dot plus A3 E3 hat dot. So the unit vectors themselves can have a time dependence, and that's something that we have to take into account when we work in curvilinear coordinate systems. So let's see what that actually looks like in the case of polar coordinates. We have in polar coordinates, our coordinates are r and phi, and the unit vectors are r hat and phi hat. So we'll bring in this. And let's say that we have a vector that moves in time, a position vector of some object that changes over time. So this is r at time t, and this is the vector r at time t plus dt. We have unit vectors that go with this. This is r hat of t, phi hat of t over there. R hat of t plus dt, and here's phi hat of t plus dt. I'm going to call this angle in between here delta phi, and delta phi is just going to be equal to the angle at t plus dt minus the angle at time t. So this angle here is of course the angle at time t. This is the angle at time t plus dt. This is the same position, just taken at two different times, time t here and time t plus dt over there. And the unit vectors and all the angles and distances and everything change over time. Our goal now is to find the time derivative of r as a function of time. So let's just move these and scale them over on the right here. So this is now r hat at t. This is r hat at t plus dt. It's not completely obvious here, but they are the same length. So therefore we can see this as being part. Both of them are hitting the radius of us. Oh, that's really ugly. Are hitting the radius. Are hitting the radius of a circle, like that. This is supposed to be at the center of the circle. It doesn't really look like it. Well, you get the picture. I'm going to draw here as delta r, actually delta r hat, the difference between r hat at time t and r and t plus dt. And the angle here between the two is of course going to be the same as the angle between the two position vectors here. So this is delta phi. We can now write that delta r hat is, in terms of delta phi, it's going to be the length of the circle segment, which is 1, times the magnitude of this angle, which is delta phi, and then we need to have a direction. Well, the direction that delta r hat is pointing in is clearly phi hat. Okay, this is the circle radius. From this we can see immediately that we can take delta r hat, we can divide it by delta t. That's equal to delta phi divided by delta t times phi hat. Now, because of the way we define delta r is also defined as, write it down explicitly, r hat at t plus dt minus r hat at t, and the same thing for delta phi. These will actually tend to derivatives when delta t goes to 0. So we will get then that r hat dot, which is equal to the r hat dt, is actually equal to phi dot phi hat. So that's the expression for the time derivative of the unit vector in the r direction. Perhaps not what you expected. We can do the same thing for phi and phi dot. I'll leave that as an exercise to you. But we can show equally well that phi hat dot is equal to minus phi dot r hat. That makes sense, right? The unit vectors depend only on phi, they don't depend on r. And delta phi hat, the difference between this vector and that vector, is actually going to be pointing inward. Okay, so we get this result as well. That brings me to my second question for this video, and that is there a different way in which you can find r hat dot and phi hat dot, other than the ones that we done it here? Here we used a geometric construction, but my question for you is, can you find r hat dot and phi hat dot from the expressions for r hat and phi hat? That is a little easier. We'll talk about that in class as well.